down to what is the quality of the underlying network, and that affects what the packet losses are, the variability of delay, the maximum end-to-end delay, and what we want to do is come up with some recommendations. So to finish this discussion, here's a list of the conventional wisdom for how to try to achieve voice quality. Number one is use the G.711 codec, in other words 64 kilobits per second, and get that working first. And yes, this is more bits per second. In fact, it's the same as traditional telephony, but it's got the lowest delay and it's the most robust. It's not that sensitive to packet loss. We want to keep the packet loss below 1% and no consecutive packets. And the way that we would end up tweaking that would be tuning the size of the jitter buffer and making sure that the underlying network is designed properly so that during peak times of the day we don't end up having over congestion and data starting to be discarded or overwritten in buffers in the middle of the network. So it comes down to network design and then jitter buffer to correct any variabilities within that design. And we want to turn on the interpolation. This is called packet loss concealment in the voice over IP world, so that if we lose a packet, then we can try to guess what it was supposed to be. We want to keep the chunks of speech relatively small, so that if we lose one, it's not such a big deal. And the standard technique is to put about 20 milliseconds worth of speech into one real-time transport protocol data unit. Now there's something that you could tweak here. When we start talking about these protocols, and we went through this in a previous discussion, we take the output of the codec and we give a chunk of those bits to the RTP, the real-time transport protocol. It puts a timestamp on there. And then we take that and give it to the UDP protocol, and it puts a sequence number and error check on there. Then we give it to the IP protocol software that puts that in an IP packet and puts the IP address of the destination on the front. And then inside the building, that goes into an Ethernet LAN frame to then be carried across the twisted pair cable. We want to make sure that these things all exactly line up. The UDP payload size is exactly the same as the size of what's coming out of the RTP protocol. And we've got our IP packet size set so that one UDP protocol data unit fits exactly inside one. And we've, if we can, got our frame size set so that one IP packet fits exactly inside one frame. Because otherwise you end up with scenarios like we made a mistake and we've got our packets set so that they hold 64 bytes, but the frames only hold 48 bytes, just as an example. And so anytime you want to send a packet that goes in a frame over a physical circuit, you got to take the first 48 bytes of the packet, stick them in a frame, transmit it, and then you have to take the remaining 16 bytes of the packet, stick that in another frame, pad the rest out with zeros, and then transmit that. And at every intermediate point, it has to receive both of these chunks to be able to reconstruct the packet, to look at the IP address, to make a route decision, then chop it back into two pieces and send them one after another. And that's going to wreak havoc with our delay and our jitter. So we want to make sure that all of these protocols are set in software so that they all exactly line up with payload sizes. And these would be detailed settings in your software and in your routers. We want to make sure that we do not exceed end-to-end delay specifications, because otherwise people are going to hear echoes. And the design maximum recommended is 150 milliseconds. Now, if we start having problems with losing too many packets, then we have to start looking at mechanisms for correcting this. The simplest way is to have infinite bandwidth between the locations. Is just put enough underlying horsepower underneath these IP packets that there is no congestion. And if you're Verizon or AT&T or MCI or Global Crossing, you can be pretty sure that that's what's going to be done to start with. Is we'll just put in enough capacity so there is no network congestion. But we're still going to have congestion at things like routers and Ethernet switches. If we want to start dealing with congestion, then we have to start limiting the amount of traffic that gets transmitted. One easy way to do that is to limit the number of simultaneous phone calls. And this gets back to our gatekeeper with the admission control function. Well, if things start degrading, then the gatekeeper won't let anybody start a new phone call using voice over IP. Maybe we'll end up having traditional telephony for the overflow phone calls, if you want to think of it that way. Another thing that we could do is prioritize voice over data. And we're going to look in the next discussion at techniques for giving packets that have voice in them a higher priority than packets that have data. And so if congestion happens, the data packets get overwritten and disappear, not the voice packets. And then there's even brute force stuff, is that we don't want to have a low capacity circuit. When we're looking at designs proposed by this vendor and they say, well, you can save a lot of money by putting everything over a T1, all of your voice and data, and what we'll do is we'll have your data on 12 channels and then the voice on another one, so that's how we're doing prioritization. Well, you have to actually sit down and do the math and see whether there are enough bits per second on your access circuit to handle the peak load. You can't just listen to a sales pitch, somebody waving their hands around and saying typically this and typically that. Somebody has to sit down and check. There are some other techniques that we could do. If you think back to our protocol stack and all of the overhead that gets added, we've got the output of the codec, then we've got the RTP timestamp on there, the UDP header with the sequence number and error check, the IP header with the IP addresses, and then the LAN information on there. And there's quite a bit of overhead sitting on top of the payload. There are techniques to reduce the header down to just a few bytes. What does that cost us, though? Delay, because we have to reconstruct all of this at the far end. We have to do compression and reconstruction, so it introduces a bit of delay. As you can see, there are trade-offs here, and the trade-offs are going to be different for every implementation because it really depends on the network, both the local network, the Ethernet at each end, and the wide area network. It depends on the loading of the network. It depends how the jitter buffers are set, and it depends on the coding techniques that are used. So there's no magic formula. You really need this in order to get voice over IP quality.